In this video, we are going to discuss about the high frequency analysis of FET. So, on the completion of this topic, the students will be able to demonstrate and construct the frequency response of both BJT as well as the FET amplifier at various frequencies. And common source amplifiers at high frequencies. So here we can see the circuit diagram, that is small signal equivalent circuit of the common source amplifier. So since it is a common source amplifier, we are grounding the source terminal, that is CGS, CGD and CA. So here you can find out the capacitance in the CGS, that is input side, and the feedback capacitance, which is CGD, and here you can find out the output resistance, that is CDS, and this resistance, drain resistance RL and V0. So here you can find out that Y is equal to 1 by Z is equal to YL plus YDS plus GD plus YGD. So this four things you can find out the admittance corresponding to the load resistance, which we call it as YL is equal to 1 divided by RL, and the admittance which is corresponding to the CDS is YDS is equal to J omega into CDS, and the conductance which is corresponding to RD is GD is equal to 1 divided by RD, and YGD is equal to J omega into CGD, which is the admittance which is corresponding to the CG. And to find out the voltage gain, there is the voltage gain for the common source amplifier circuit with the load RL, which we are giving as AV is equal to V0 divided by, that is output voltage divided by the input voltage. So we write this equation as IZ divided by VI, which is equal to I divided by VI into Y. Substituting those values in the I and Y in the above equations, we will be getting as AV is equal to minus GM plus YGD plus divided by YL plus YDS plus GD plus YGD. So at low frequencies you can find these values, that is YDS and the YGD is equal to 0, so that this equation will be reduced. So we get the equation as AV is equal to minus GM divided by YL plus GD, which is equal to minus GM into RD into ZL divided by RD plus RL. In case if it is greater than, means we can neglect those terms, we can write it as minus GM into ZL dash. So ZL is dash is equal to RD parallel to Z. And this input impedance we are calculating as Yi is equal to YGS plus 1 minus AV into YGD. To find out the input capacitance in the case of the Miller's effect, we are splitting into two terms, that is one along the input side and one in the output side. So that if there is increase in the input capacitance over this capacitance from the gate to source, which we call it as Miller's effect. So this input capacitance which affects the gain at the high frequency, we can be taking the calibration of the cascade and amplifier. So in the case of cascade and amplifier, means the output from one stage which you are using as an input to the second amplifier. So this input voltage of the second stage, which we act as a shunt, also it is present across this output of the first stage, as well as it is shunted by the capacitance of Ci. So output admittance, we know if we are calculating the output impedance, we will be setting the input voltage as 0, that is Vi is equal to 0, which is nothing but RD, CDS, CGT in parallel. So this output admittance with RL, which we are considering external to the amplifier, is given as Y0 is equal to JD plus YDS plus YGD, and in the case of the drum and drain amplifier, which we are calculating in the high frequencies, the equation of the circuit is given here. It's a fixed circuit. So here we are drawing the small signal high frequency equivalent circuit for this common source amplifier, source follower, which is that is a common drain amplifier, and here we are calculating the voltage gain. So the output voltage V0, which we are finding from the product of the circuit short circuit, as well as the impedance which is present with the terminal source voltage gain, which we are giving as V0 is divided by Vi equal to GM plus J omega into CGS divided by RS plus M into GD plus J omega into CT. So at low frequencies with this gain which reduces, so we can reduce this term, that is AV is equal to GM into RS divided by 1 plus GM plus GD into. And input impedance we are calculating by applying the Miller's theorem, that we get the Yi is equal to J omega and CGD plus J omega and CGS minus A equal to J omega and CGD, which is A output which is 1. And output admittance we can be considering external to the amplifier, which we are giving as Y0 is equal to GM plus GD plus J omega CT. And the frequency response of the common source amplifier, which is for RC coupled common source amplifier, is given, as well as the high frequency equivalent circuit, which is given here. And this shows that the high frequencies which is coupling and the bypass capacitors will be acting as a short circuit, which will not affect the high frequency response. So that this one shows the equivalent circuit which is showing the internal capacitance which affect the high frequency response is given here. So see in Miller we are dividing in two parts. One is in the input side and the output side. So see Miller input is equal to CGD of AV plus 1, and output side will be writing as AV plus 1 divided by AV. Here we know that CGD is equal to CRSS, CGS is equal to CISS minus RS. And input network we will be calculating the F frequency, that is F is equal to 1 divided by 2 pi into RS parallel RG into CT, where CT is equal to CGS plus CN, which is Miller effect, and the output RC network with the current source we will be calculating as RD parallel to RL, and the output side we will be calculating in the CO terminal and simplifying the circuit in the case of output network. Thank you.